1989, and I came here for a job interview in 1990, a year later, and I remember in my job interview asking people here, what do you guys work on, right? This is before the web, right, was invented, so you didn't know what people were doing in faraway places. And people here said, oh, we work on cellular radio. And I was like, huh, that's so interesting. I've never heard of people who work, who do cellular radio research, right? It was completely foreign. I mean, he was just one of a small handful of students, maybe in the world, working on wireless. And and in fact, not only was he early, but he was kind of profoundly important to WinLab. In 1992, I think, he came to WinLab as a grad student visitor, and he helped design and build our first mobile wireless simulator for doing channels and power allocation, and much of WinLab's research in the 90s was the experiments were all built on extensions to the simulator that he helped us first design, so anyway, since then we've had kind of 20 years of the benefit of his advice and guidance, and he's been profoundly helpful to a variety of grad students over the years. And, so it's really my pleasure, and I'm really looking forward to hearing his keynote talk, which is a pathway to 5G. Please.
Thanks, Roy, for the very nice introduction. So I'm at Ericsson Research, and I'm leading a lot of the work that we do towards 5G. So I often get this question, what is 5G? And it's not that easy to give a good answer on that one. It's sort of, you can always bring this trivial, whatever comes after 4G, right? But really to go into to really say what it is, it's hard. So I will now try to share Ericsson's view on what we could expect it to bring, and a little bit on how the solutions could look like. But this is really work in progress, right? So we will have a lot to discuss in the next coming years here. So looking at Ericsson quickly, I guess you know us as a sort of mobile vendor, infrastructure provider, but equally large within Ericsson is actually the services business. So running the networks is getting much more important for us. And lately we have invested in media delivery, BSS, OSS kind of management things, and this is really also sort of increasing. And I think this is a clear trend looking forward to 5G. I think it will be much more run as a service. So different companies will provide these networks, and they will be run as a service for different industries to connect to. So it is really turning clearly into a services business, as everything else, I think. And then especially interesting here in the US is of course that our San Jose site is sort of a second headquarters for us, and they are really focused on the IP and SDN and the media parts. Ericsson Research, we have organized ourselves in this way. So we have the radio access technologies in my area, the wireless access networks. So this is the sort of the radio parts, right? But then we have the IP and transport parts, we have the cloud technologies, services, media, network features, sort of building the complete sort of infrastructure. And then we need the security, the sustainability, and the management of all of this. And this has to go on top of hardware and software technologies. And I would like to argue that we really need to have all of these competences in order to really drive and design sort of what 5G should be. So it is really a much broader approach to this than just the radio access. So here we are then, 1, 2, 3, 4, 5. And what is really here the story? I mean, I started at Ericsson in 1994, so I joined here on the 2G. GSM was already there. You had IS-95 coming up, and my first task was to argue against IS-95. So we had all of these fights of the conferences, and that really led to the choice of the wideband CDMA, right? That was sort of the IS-95 was really the key thing to go for the wideband CDMA networks. And going from 2G to 3G, we were not really clear on what we should use these systems for. We had this killer application of video telephony. And I think I used it once back then or something. It was not really the thing. And then after a while, we just realized it was internet access and mobile broadband, as we call it today. That was the killer application. With HSPA sort of adjustment to that, it really became the first networks that really could support mobile broadband. And then these WiMAX guys come along, right? Starting to talk about OFDM and how great that was. And that really led to the LTE systems, right? That we decided, yeah, we should have these OFDM systems, of course. And then we sort of designed the LTE and the LTE Advanced, and then we were very clear on what to use it for. It was really to optimize for the mobile broadband services, right? So now when we should go into 5G, I don't think we see any major sort of enemy or competing things. I mean, all the operators, all the vendors, all the different parts of the world, everybody's into the LTE evolution at the moment. So it's not this external force that makes us go forward. I think we are not that clear either on exactly what we should use this for. Of course, we will do much more mobile broadband and so on, but what is exactly the requirements on this 5G? So in that makes it a little bit the same situation when going from 2G to 3G as we now are facing here going to 5G. So let's see a little bit on what this should be then. Before going into the 5G thing, there's a couple of things that we need to set the scene a little bit. What will be the situation 2020? So going to 2020, we are releasing this mobility report where we are trying to make an estimate or a prognosis of how the traffic will evolve. And we see here that the mobile data traffic in the networks will continue to grow exponentially. So we are estimating that it will grow 40% year on year. And over this 6-year period then to the end of 2020, when these 5G systems should start to be introduced on the market, we should have like 8 times the traffic we have today. And only the increase between 2019 to 20, that increase is more than all the data that we had delivered up to 2013. So it is really this exponential growth on this still, right? And of course, it will be dominated by the smartphone users. Today they are consuming like 1 gig a month. They will go up to 3-4 gig. But we also will have tablets and PCs and other equipments connecting to these networks. So how do what would the situation look like then 2020? I think the operators would have reformed most of their spectrum to LTE. So they will use all the spectrum they have today to LTE. They will have to get new spectrum to put into and drive more bands in order to provide with this capacity. And I also think that we have seen the small cells taking off. We haven't really seen that yet. We're talking about these small cells and the HETnets and so on, but the market is still fairly small. I think in this time frame we will see this densification of the networks as well in order to meet this demand. Another thing which is happening, which is a little bit harder to grasp. Let's stay with this one first. This is how the subscriber will evolve, and this is North America. And the number of subscriptions will increase, of course. And you can see how almost all of them will be over time sort of be connected over LTE networks. And if you were to look at the data consumed or delivered, it would be even more dominated by the LTE technology, of course. It's hard to really these are mobile broadband users, and you can make sort of smartphone users, and you can make some broad segmentation of the market. But it's more and more that every user is combining what he or she likes. Somebody likes a sort of the music app, and somebody is a lot at home, somebody is traveling. So it's getting more and more unique characteristics. So we are saying that this segment of one is sort of appearing, that each user is very individual and using these systems in his own ways. So it's hard to segment it. So this is what we see on a mobile broadband side. The other thing, which I was starting to talk about, is how is this transformation of ICT changing the society? So there is this theory, right, that first in an infrastructure, you have an installation phase where you're installing the stuff and establishing and then it becomes generally available. And on top of that platform, other industries start to innovate, and it's transforming a lot of other segments in society. I think the power grid is a very good example, looking in the past where you were building out the power grid in order to have electrical lighting, and then you figured out that you can use it for heating, and now we're using it for everything. It's sort of a foundation for all we do, that we always have electricity available. The same thing is now with the mobile broadband. And I think I would like to argue that we have actually passed this inflection point already. Some industries has already transformed. Music industry, I guess, is the best example. Is shipping CDs to streaming music. We see the TV going from sort of broadcast to on-demand streaming TV. And I think more and more industries will go through this. So this is also now happening these coming years, and this will be much clearer after a few years now, before we have the 5G systems on the market. So what really is happening here is that we have the mobility, that everything can be connected, that moves around through over these broadband networks, and we will have all these applications on this cloud environment, and that really becomes a platform for all other industries to transform in the way that they do their business and so on. So given these two things, we get to 5G then. What to expect out of 5G? And I think it will be a multi-dimensional performance and energy performance which is significantly higher or better than what we have today. It will be this foundation for other industries to efficiently transform their businesses. And there is a very strong need to have discussions with the future customers of these networks, that is other industry, society, that should use these things in order to together with them create this global standard that this has to be to build on. And when we have done that, we see that we should have this massive machine type communication should be facilitated, the critical machine communication should be there, and we should be able to do this mass market personalized TV on top of these networks, and much more as well.
Massive machines.
Yeah, that's a sort of, I will come to it, but it's a large number of smaller devices connected, so massive in numbers. So looking at this multi-dimensional thing, and this is sort of our input to ITU, and I think it's converging to something like this. So we will see a little bit like times 10. So if we can do 1 gigabit today, we will aim for 10 gigabit per second as a data rates that we should provide. If we can get latency down to 10 milliseconds, ideally today, we will go for 1 millisecond. So there's a little bit times 10 in all of these different dimensions. Then of course, the connection density, here we will really take a step change compared to today, really to support this. So 50 billion devices, connected devices we talked about in the beginning, and now we are of course increasing that number if you're aiming to the lifetime of these systems. Energy efficiency is something that we have not really focused on when we design previous systems. So here we can take very large steps, I think. Then spectrum efficiency, that becomes harder and harder. I think we still have dimensions when it comes to utilizing beamforming and antenna dimension a little bit further. So we will do a little bit on spectrum efficiency as well, right? And the use cases, again, the use cases we foresee now is the mobile broadband services, however they will evolve. You can think Google Glasses, augmented reality, I mean, all of that that you can imagine. And then these two more machine-focused use cases. So I don't know, but I'm pretty sure that this is wrong, right? That this system will be used for something more as well, something that we haven't really thought of at all today. So it's a huge need to be flexible and understand that, yeah, this puts requirements, that makes it interesting, so on, but it might take other turns. So save this slide and then you can bring it up with me later on. So talking a little bit about these machines. So here we started off, yeah, we should connect a lot of machines, and then we're starting to realize that these machines, they are very, very different. The differences between the needs and characteristics of different machines is much, much larger than looking at different mobile broadband users. So just to segment or say that we should connect machines, that is not really enough. And then we have at least got to this stage that we see two groups. So the massive number of machines, here we have sort of a huge number of sensors, actuators, and these are typically sort of low cost. They should be low energy, they should be able to run on a battery for several years. They don't transmit that much data typically, so small data volumes, but they are large numbers. And in many cases, you really need a full-blown sort of coverage for these things if you really would like to support full mobility of connecting these things. So if you will have different goods that you connect, and you will really like to monitor them when they leave the factory and they reach the store, and then when they get home to the consumer and so on. So there is a wide area requirement on this. And here, this one is actually what it started already. So here we see already now that LTE is developing towards this, because it's so natural to think that you would like to utilize the existing infrastructure that is being built. And on the same infrastructure as we have the mobile broadband, you would like to carry this machine type communication as well. And then LTE was not really designed for that, so we need to do modifications to LTE in order to meet these requirements. And of course, there are limitations how far you can go. So I think we will come quite far on this, but it will still be so that the smallest temperature sensors will not be able to carry an LTE chip, so to say. So then we're thinking that we can have some capillary network designs where we have a gateway which can talk to all the sensors. The gateway could be backhauled into the system by LTE, for example. But I think all the important things, sort of Internet of important things, should be able to be connected here. And then there will be, of course, complementing capillary networks in order to connect the rest. Now in research community, I think the focus is shifting to this critical machine type. So a lot of new research projects, consortia coming up when it comes to looking at critical communication, critical machine type communication. And here we are looking at these self-driving cars. We are looking at automation within factories, robots that are communicating with each other, solving different problems. And we have this tactile internet that the delay should be so short so you can get this touch and feel of things, right? And here we talk about delays in milliseconds. And we are talking about very, very reliable systems, and where you can make perhaps extra investments to get full availability in certain areas where you would like to run these services. And I think when we work more and more on this, we will see that this will segment into sub-segments as well. So looking a little bit at the latency reductions that we have seen with all of these different systems. So if you really are theoretically, I guess in LTE you can send it's a time slot of 1 millisecond in LTE, so you can send something, process, get it back. So in theory you can have a round trip down to sort of 10 milliseconds. And then we would like to go down even further on that. And then obviously the shortest time slot that you have on the radio will need to be much shorter than that. So here we see requirements which is not that easily fit into an LTE evolution. Another thing which connects a little bit to this software-defined networking or software-defined wireless networking, is that we really need to understand how to do these systems much more flexible. So we would like to have some sort of API or environment where different industries can come in with their requirements, and you can program the network. So you can really make sure that the network can provide sort of the memory storage, the memory computation and communication capabilities that exactly needed for that customer with its connected things. And then, of course, it has to be agile and sustainability and all of that. It also has to be robust in the sense that you need to be able to offer a service for a small company doing something on a campus, or a multinational company that would like to keep track of all its assets in a global way. So this scalability of these solutions will be key. And when companies start to connect their assets into these systems, the security will be even higher, the requirements on that. And I think also these other industries, they need to feel that this is a standardized, predictable platform in order to go for this solution. So I think we see a little bit different type of dimension, a little bit more softer dimensions than the ones that we have talked about, just bitrate and delay and so on. Another aspect is of course that we would like to avoid doing separate networks for every different industry. So we would like instead to make a network that the operator could have one network serving many industries. And then of course each industry, each customer would like to have its sort of slice through this network in order to have its performance. And if you can achieve this, it should be much more cost effective, and industries which cannot afford their own vertical should still be possible for them to connect their things in such an environment. So I think this is important. So this was a long sort of wish list on everything that we would like to have. So then we are...
So that's kind of communications cloud, you might want to call it? You can slice and dice it.
Yes, exactly. I think these different industries, they will have their own clouds, but we will also have sort of a cloud within this network. Sometimes we call that a local service cloud or a distributed cloud, where we have storage and computation within the network that could be programmed to specifically support the different needs. And obviously, if you want to do really, really short delays, you need to push applications further up.
I mean, I see what you're saying, it makes a lot of sense, but it's really counter kind of like intuitive. You're trying to sort of improve the performance or delay latency, but you're trying to sort of expand a sort of a hammer for everything.
Yeah. But I think with the concept of having different slices, I think we could have, I mean, the most important to share is of course the radio side, because the base stations and that, they're very expensive to make multiple of these, right? If you would like to have specific core network functions, that's easier to achieve as a slice of something, or you can think of even having a little bit separate core network functions if you have really, really specific needs. So I think I'm trying to meet that with this flexibility and programmability of this thing. But it's still a wish. I mean, all of this is easy to agree on because we haven't really made any compromises. Everybody have just get all the requirements in, right? And everybody agrees that this would be great. So the next question is, of course, could we build something that could meet these expectations? And now the interesting part starts, right? So how to do that? And we don't know, of course, yet, but I think we have at least boxed it a little bit, so we believe that it will be radio access needed for this. I will come into that more and more. Now, next slides. This has some IP infrastructure, because we have enormous high data rates being pumped over these radio air interfaces, but the IP infrastructure will be the next bottleneck most likely. We would push the cloud infrastructure. I mean, that's already happening. The core networks of today is being cloudified within the operators, so that we have already started to introduce sort of cloud environments into this, and the network application is then virtualized running on top of this cloud. And that will happen before 2020, I think. Then, when we have done all of that, I think we will realize that, shit, this needs to be managed and orchestrated in some way, because now it becomes very, very complex, and we are asking for extreme performances. So I agree on your point that it will be that this will really be a challenge to get everything of this to work and to get all the performance out of this. And let's see how far we can come on that. Security needs to be everywhere, and sustainability will be much, much more taken into account, not sort of wasting energy unnecessarily here. And all of this sort of is the 5G network. So, going to the radio now. And this is, I think, is the core. If you should remember something, look at this one, because this is sort of, I think, the really summarizing the strategy that we're having now. And I think it's not only Ericsson, it's most major players are agreeing on that it would look something like this. So we will have the LTE evolution, and the LTE evolution, that will be, as I said, that will be deployed in many existing spectrum bands by 2020. Will carry an enormous amount of traffic. So here you really would like to be backward compatible, meaning that you would like to introduce new features, and all the old terminals will still work on the same carrier, so you don't dividing your resource and anything, and not having to reform and so on, because this will be heavily loaded the system by then. Then we realized that the LTE evolution with these backward compatibility constraints, that will not solve the problem, so we need to look at new radio access technologies. And obviously we think that we need to go up in higher frequencies, because if you want to do 10 gigabit per second, you need a broader carrier, and that you will not find on lower, so you need to look on higher frequency bands. So obviously we need something new which is designed for something that could work on higher frequencies. And here we don't have any backward compatibility constraints, so here we should optimize for performance, and then we need to make sure that this really works good together. And one thing which I will show later on, that if you have sort of higher frequencies and it's really hard to build a consistent coverage solutions on top of that. It will be more patchy. So having the possibility to load balance and steer traffic between sort of low and high bands will be key here. And then of course over time there are great things. This is a new system, equipments get old, operators are anyhow shifting, so we will have a migration, of course, from the new to the old over time. But we don't see that we will do a 5G that will completely replace 4G. So yeah, so this is, and then what is then exactly this new RATs and the LTE and so on? One good thing is to look at what's actually going on now. So on the LTE evolution, we have just completed release 12, and we are just about to start release 13, and that will continue 14 and 15. Yes?
I just had a question about your previous slide. So you think that picture is, yeah, so this whole thing is going to happen by 2020, or is that the expectation? Because you had this initial slides on 2020.
Yeah.
So
I think the LTE evolution will continue from now until 2020 and beyond 2020, so that will just continue. This new RAT coming, that according to the time plan and ITU time plans, that will be able to be approved as a 5G technology in 2020. Hopefully there will be spectrum on the market as well, perhaps 2022 or something. So I guess we will see fairly large trials and things going on before 2020, but the real take-up might be 22 or something, but in the order of 2020. So before then, we will have what's happening on the LTE side, and now we have the license-assisted access coming up in LTE. So we will be able to operate in unlicensed bands. I think this is just the start, right? We will say 5G will be able to handle all different spectrum flavors. So we'll run over unlicensed, shared, or dedicated spectrum. The multi-antenna techniques are already quite advanced in LTE, and they will continue. So we will have this 3D beam forming. We will start to form beams in all dimensions. The massive MIMO will be there, but it will be less massive than in 5G. The new RUTs will be even more massive, but it will go up to 64 antennas or something like that. And we'll continue on this different comp solutions. Small cells will be there. Latency reductions. What can you do within the standard, within LTE? And I think you can do quite a lot. We have already started work towards machine type. That will continue. So I think we are addressing these drawbacks of LTE that we didn't think about this use case when we designed it. And we're also opening up now so you can have device-to-device communication within the network. So that will already be a first version in release 12, and that will continue to be included. So you can also support a device-to-device application. And the use case in the first case here will be the national security, public safety type of applications that is asking for that. But there's also discovery, so even if you're not communicating, it could be a discovery mechanism to see that your friends are close or whatever. So there's a lot of different things that can be built on top of such capabilities. So this is happening already on the LTE side, and I think this gives a good clue where we're going. So what do we have then on top of that? So we are seeing that we have these key technologies that we're believing in for 5G. So I talked about that we should go to higher frequencies. Going to higher frequencies means that we will need antennas. So higher frequencies, beamforming goes together. The spectrum, we will need to handle a lot of different spectrum. A lot of the new spectrum higher frequencies will for sure be shared or unlicensed. The multi-site, we are seeing that we are connecting to many different access points. We need that in order to build this reliability and robustness we are looking for. It's also so that this device-to-device and this, we are thinking about self-backhauling, so access and backhaul should be done in the same system. All of this is generalizing this cellular concept, right? That we have a base station and a terminal, and that's the only communication link. Now we have a lot of different communication links in this system. And then you can think of, okay, we can do that. We should just increase the number of control channels, but that's exactly what we should not do. We should really think to make an ultra lean design to reduce everything which is sent unnecessarily. And that's the key thing in order to reduce interference in all of this. It's also then a key thing for getting the power consumption down when you're not transmitting data. So I have a little bit on each of these now. So the spectrum side, it should do licensed, unlicensed, shared. We think dynamic TDD. I think going up in frequency, it will be more and more TDD rather than FDD because it's easier to get an unpaired band. But we don't want to have this strict division of uplink and downlink then, so we would like to have that more dynamic. For some backhauling links where you have perhaps a surplus of signal to noise ratio, we can even think about having the full duplex if you can sort of handle the interference cancellation scenarios. This ultra lean, we would really like to minimize this always on. So we should try to get rid of reference signals, sync signals, broadcast information that is just transmitting all the time today. And this will then reduce energy, it will minimize interference, and it will also make it more future-proof, because if you haven't standardized anything, I mean, you could add things easier to the standard if you haven't really filled it up already from the beginning. The multi-site, we talked about that, so It will be very much more beam forming, so you will have different beams that are being tracking the users coming from different sites. So I think this beam tracking and this multiple access points communicating to the users is needed. And it has really to be rapid. We foresee that this propagation environment, it will be really rapid changes. So you have, for a few milliseconds, you have a beam from here, and then something happens, you have a beam from here instead. So that will be a big challenge. And I think this multi-layer, multi-low and high frequency bands will be key in order to make this. The beam forming. The good thing going up in frequency is, of course, that the antenna elements get smaller, but then you're losing in path loss, of course, so you need to make the antenna larger. Then and that you do by adding more antenna patches, and then automatically you get this beam, more narrow beams, of course. And I talked about the device-to-device in these systems. So these are sort of the key technology components that we are trying to integrate into this system. Then we start to look a little bit, what could these systems provide if we are successfully managed to build it? So first thing we looked at is, okay, let's assume that we get some spectrum on 10 gigahertz. Can we still make an outdoor to indoor system? That is, could be an outdoor deployment and still serve users indoor? Would that still fly? And I think when we looked at this, we looked at this 21-story building there, this office building. We put the micro base stations outside, line of sight, looking at the building. It has 2 watt transmit power, it has 100 megahertz of bandwidth. And the building is sort of a concrete building with normal glass. It's not the metal coated glass, because then it will be too hard. Then for these buildings you need to go indoor, I think. But for this case, it's sort of feasible. You can put the antenna towards that building and you will penetrate in the building and you will provide this data rate all through the building basically. So it is still feasible on these frequencies to do an outdoor to indoor deployment. And what capacity would that then bring? So we were really thinking of what should we use all of this capacity for, and again, knowing that we are wrong, we still sort of made a guess here. So the bottom line there, you see, which is almost sort of zero, that is the mobile broadband traffic. We extrapolated that from 2020 to 2025. And then we added 25% penetration of 4K video, 3 hours per evening. So we said that sort of 25% of the customers, they don't have fiber to their home, they would like to have 4K video, and they are consuming this 3 hours at the same time, all of them in the evening. And we would like them to provide 10 megabit. So we would like to do this with 95 capability. And then we will get this other demand line here. So you say, this is a completely different scale than this one. So today's problem where we are trying to understand if it is possible really to meet this one. But this is like looking at sort of voice traffic in today's mobile data. So all things we do today will be like noise. And it will be totally dominated here by this TV consumption, if you, for example, believe in that. So how could we build such a system then? So what you need to do, first you need to reform everything. So you need to have to get 80 megahertz below 2.6 gigahertz here. And you have an inter-site distance of 300 meters. So typical European city density. And then you need to add another 80. Perhaps you can get these on the 3.5 gigahertz band. And it improves a little bit like that. Then you need to densify your network, so you need to go down to 200 meters. And then 2020, you buy 5G and turn that on. And if you then have a 500 megahertz carrier at 10 gigahertz, do carrier aggregation between the new and the old, then you will get this sort of capacity. And then that increases slowly here. That depends on that we are building indoor systems like year by year here, increasing the number of buildings that are sort of covered by an indoor system. So they are sort of, that traffic is sort of handled. So this is an illustration of what we could use this for. Yes?
So this big jump is from carrier aggregation. You have this big jump there.
Yeah, the big jump is that you get 500 megahertz, new 500 megahertz that you turn on. That's the big thing. But just turning on that system will not work, because the coverage from that one will be too spotty, to scatter, to fragment it. So you really need to carrier aggregate between your old and your new system. And then you see that this provides like 10 times the capacity of this one. So if you have coverage of the new system for sort of 90% of the users, and 10% needs to do a fallback to the old system, then that match a little bit. So you need this capacity difference between these two to match a little bit. Yes?
You say desensitive transfer.
Any particular reason that you choose NVIDIA as an actor?
Yeah, I think it's of course easier to get an outdoor to indoor penetration on lower frequencies. So I think this could work on 15, 20, perhaps up to 30. We have looked at all of this. It will not work on 60. So yeah, we wanted to show the best case here. So that was the reason why we took a little bit lower. Yeah. Then of course, if a lot of spectrum were available on lower, of course we should go for that. But of course, the likelihood of getting sufficient bandwidth will increase if you go up a little bit. So that's the trade-off.
Desensified, is that the receiver sensitivity for 4 or 5 dB lower, or what does that mean?
No, densification. It's, you put it the more cells altogether. You add more cells. So we have gone here. We have added more. Yeah, densification. Yeah.
And for density sense.
Yeah.
So is this really a new rack at 10 gigahertz, or are we really talking carrier aggregation? LTE waveform, maybe it's different numerology for OEM, but it's still within the LTE realm, or is this completely new rack as we consider this now?
Yeah, that's exactly what we don't know yet. I think that when we simulated this one, we have not all the details in, so you can say that this is just sort of an upscaled LTE type of network. We just think take LTE times 5 or something, and then we just did that. So here it's what we simulated is sort of LTE-like. But I think we haven't really looked at all the mobility aspects out of this. How quick, how should the MAC protocol really work, and what retransmission schemes should it be, and so on. I think there's a lot of things here which we have not really looked at enough. So I foresee that this new RAT will be different in a number of aspects compared to what we have. But we would like to do the new RAT in such a way that we have a few, perhaps only one, and we can make it sort of scalable, so you can have the new RAT on higher frequencies, on mid frequencies, but also migrate into lower frequencies.
One more quick follow-up question. So we talked about this new rack, when you start to bring in the new rack and the just talk about multi-layer connectivity, right?
Yeah.
To get umbrella coverage in the low frequency spectrum. What do you see in terms of inter-rack now? Today inter-rack is seen as 2G or 3G or 4G. Seems like you need to really bring a lot more interaction between these different racks.
Yeah. Yeah, I fully agree, and that's exactly why we think about this definition of 5G as being the LTE evolution and the new one, and on all these multi-RAT things should be integrated and built in from the start. It has to be much tighter. We need to control the traffic between these layers much more efficient.
What kind of antenna did you enjoy or handle external because of the gain and
This this antenna here, it was not sort of an extreme beamforming thing. It was sort of lighting this building basically.
Measurements or, are these measurements results or estimation?
These are propagation models based on measurement, but then we taken the propagation models into the simulator and then simulated this. So it's based on simulation, and there's an antenna in there which is basically pointing towards this building. So it's not like this has 100 beams pointing to this building. No, it's a sort of one sector pointing towards this building. So that's kind of antenna.
What is the distance between the antenna and the building?
Yeah, I think it's sort of 50-100 meters line of sight. So this is a good case. It's much harder if you hit the building with another angle and so on, or so on. Yeah. But think about the below rooftop type of thing towards another building. So then we continued, and so we have started building a little bit of things. So we have our 5G radio test bed, and this one we had a press release this summer saying that we can do 5 gigabit per second. And what this is then it actually is, so you can see the terminal here. This is the terminal. It moves around in our experience center. This is the antenna on top, and this is sort of a big rack of baseband cards. It takes a lot, and there's add on a lot of antennas and stuff. A screenshot showing that we can do 5.8 gigabit per second. And what it is then, so here you see the carrier, and we have 400 megahertz bandwidth at 15 gigahertz. It's not that we are saying that it will be 15, right? It's something that we could get, and it's in the lower range of this. It has centimeter wave. It's not in the millimeter wave range. We think this is interesting to look at. And now we will make an outdoor installation of this one, and we will do measurements in Kista, trying to understand how the propagation channel looks like, how much outdoor to indoor we can do, and so on.
This was indoor.
This one is indoor now, so it's indoor to
Multiple antennas, so it's scattering all over the place. Multiple antennas.
Yeah, it's like, it's not extreme on the antenna side, it's like 8-16 antennas thing.
But scattering, I mean, you characterize the scattering indoors. I mean, even centimeter waves, it's going to bounce around a bunch.
Yeah, it does. It's a lot of different reflections, especially in our experience center. It's like a big metal box. That is a lot of reflections in that environment, actually. So, trying to round off here a little bit. So, the time plan here is decided more or less, right? And we have ITU. They have decided to repeat the process when they had IMT Advanced. They will now do IMT 2020, I think they call it. So there is a vision of feasibility work going on. We will have the World Radio Conference 15. This conference will focus on frequencies below 6 gigahertz. Then directly after that we will kickstart with the requirement. There will be a workshop inviting for proposals. Proposals should be sent in and evaluated. And then on this conference we hopefully can get more spectrum allocations on higher bands. And then there should be specs here that should be approved. And in order to meet this, 3GPP will of course submit the proposal. So now we're working on release 13. This is sort of pre-5G. Then we will continue with 14, 15 here, but in parallel it will be 5G study items. The study item will deliver something which is sufficiently detailed to be submitted as a proposal. And while this evaluation is ongoing here, we will continue to work on the work items here, and we will deliver something that could be stamped as 5G then. And this will of course be the first version of 5G, and then it will be continue with the 5G evolution. So from a research point of view, I don't think you should be too narrow and just think about what could we deliver before 2020, or what could be. I think research results here will be relevant to take in all continuously, so to say, in this.
So is the yellow, the green, the blue rat?
Yeah, that's. I think exactly how this will play out in 3GPP is not fully set yet. But the new rat will definitely be here. Then we have this sort of LTE evolution might go in this track. So yes, that could be a likely setup. But I mean, this is not really set yet. I think the discussions in 3GPP will start here exactly how to organize this work and so on. On the research side, we have just running the Metis project that ends now beginning 2015. So in Europe we have this 5G PPP consortium that has just submitted 16 project proposal in this Horizon 2020 call. And let's see how that goes. We have WinLab is part of the Metis 2 project. Then we can see a second phase of these things more focusing on demonstrations as well. Then things are going on a little bit all over the world here, of course. So Japan, China, they have this 5G promotion group. Japan has had their RIP and entity documents driving a lot of test activities. In Korea, we have the 5G forum and strong government push on this. Europe we talked about. North America is a little bit more scattered, but we are trying here to work with our university contacts to bring it together, and we would like to get research going and get projects going, and so we are doing this together with Qualcomm. We had this conference one month ago or a little bit more, talking about the 5G in the US. And then, of course, we have this global organization. So NGM is the operators discussing what they want, ITUR and 3GPP. So it's a fairly big machinery running here, right? So I still wanted to bring this with me. So what would you then do research on? And I think during the presentations you have already identified there is a lot of white spots that needs to be worked on. But if I would try here to highlight a few things, your work on mobility first and trying to understand how this internet should evolve, sort of future internet, the networking principles, services and security, I think this is really interesting, and I hope that we should be able to be influenced of that work and bring that into this. Software-defined networking we have talked about here already today, and understanding how that goes with the cloud and this distributed computing, how to really provide these extremely short delays. The management area will be really hard. It's also hard to do research on, I think, but all contributions in that area will be appreciated. Multi-RAT, I think we understand, but that's a key. Spectrum, again, something that WinLab have been working on quite a lot, right? Energy efficiency is something that we have really understood, and we see the need of that. Then I talked about the machine type communications. I think that's still a lot of things needed there. And then when you're approaching the physical layer, there's advanced antenna systems, beamforming, beam tracking will be very new and interesting problems, I think. And going to new frequency bands will be a lot of questions around propagation properties for these higher frequencies, and all the way down to then radio front ends and everything for this. So there is a lot of work to be done, and something will be ready for 5G phase 1 and something will go for 5G phase 2 and so on. And to summarize then, so I really feel that we are beyond this inflection point and we will see all of this transformation. So that really is a key vision of Ericsson, this network society where everything is connected. On the top level, I think these 5G requirements are fairly stable. I think this flexibility and robustness will be new properties that we need to understand how to meet. We see the evolution of LTE being an important piece of this. It's clearly so that will not solve the problem, so we clearly need new radio interfaces to do this. And there is still a lot to do on the research side. So yeah, thanks a lot.